There's a moment in history that hits you like a wave of dry heat from a wood stove in the middle of a harsh winter. The kind that makes you pause and realize that somewhere along the way we traded resilience for convenience. During the 1930s and 40s, especially in the pressure cooker years of World War II, people stayed warm with heating systems so robust that even today's grid-dependent technologies struggle to compete. No electricity, no pumps, no delicate electronics, just physics, experience and design sharpened by necessity. These systems were built to survive failure, not just function. And once you see how they worked, modern heating suddenly looks fragile in comparison. If you value history with practical survival lessons baked into it, take a second to like this video, share it with someone who appreciates old-world engineering, leave a comment with your thoughts, and subscribe to Warfront Survival. This channel exists to preserve hard-earned knowledge, and your support keeps these stories alive. Now, let's get into how these wartime heating systems were built to endure when everything else failed. Why wartime heating systems prioritize survival over convenience. In the 1940s, heating was not about comfort settings or programmable thermostats. It was about survival. Fuel was scarce, infrastructure was fragile, and replacement parts were often impossible to obtain. Engineers and builders anticipated failure as a constant companion. They designed stoves, radiators, and piping to keep working even when fires burned low, pumps broke, or winter winds shredded wooden structures. That mindset alone explains why many of these systems continue to outperform modern equivalents in durability. They were not built for luxury or speed. They were built to keep people alive. The brilliance of passive thermal siphoning. One of the most remarkable yet overlooked techniques of the era was passive thermal siphoning, sometimes called gravity-fed hot water circulation. The principle was simple but profoundly effective. Hot water rises, cold water sinks. A stove or firebox sat low in the room, often beneath floor level. Above it, a water jacket or coil absorbed heat directly from the fire. As water warmed, it naturally moved through angled pipes to radiators or wall channels, released its heat, cooled, and sank back down to the stove to be reheated. No pumps, no electricity, no moving parts. Once started, circulation was nearly impossible to stop. Even when flames dwindled, the stored heat continued to move and warm the space for hours. Compare that to modern hydraulic systems that collapse the moment a pump loses power, and the advantage becomes obvious. The hidden power of thermal mass. Modern heating often focuses on speed, quick warmth that vanishes the moment the system shuts off. In contrast, 1940s builders relied on thermal mass to store heat and release it steadily. Cast iron, brick, stone, clay, and even sand-filled cavities absorbed heat slowly and released it over time. A cast iron radiator didn't just warm a room while the fire burned, it stayed warm long after. Stoves surrounded by masonry acted like batteries, charging during peak heat and discharging through the night. For people in rural homes or wartime shelters, this wasn't a comfort feature. It was survival. Today, the same principle can be applied by placing water-filled containers near a stove, adding brick or stone around heating elements, or constructing masonry benches to store and radiate warmth gradually. Convection channels that powered themselves. Air movement in these systems was equally clever. Instead of relying on electric blowers, builders integrated convection channels into walls, floors, and around stoves. Cold air was drawn in at floor level, passed over hot surfaces, and released higher in the room or into adjacent spaces. The system powered itself because warm air naturally rises and cold air naturally replaces it. In Scandinavia, brick baffles guided air slowly and evenly. In Britain, draft warmers pulled icy air off stone floors and redistributed it without moving parts. In North America, stove shrouds directed warm air toward bedrooms and living spaces. The result was quiet, continuous circulation that worked as long as any heat remained in the stove or pipes. Combined thermal siphoning, thermal mass and convection created a heating system that ignored blackouts, frozen pumps, or failed electronics. For anyone preparing for survival scenarios, these methods offer proven reliability. They demonstrate the value of redundancy, self-sufficiency, and slow, predictable heating rather than flashy, energy-intensive convenience. You don't need to recreate a 1940s farmhouse to benefit from these lessons. Adding thermal mass near stoves, building simple convection sleeves, or installing a gravity-fed hot water loop in an off-grid shelter can dramatically improve heat retention and resilience. Wartime heating systems were not built to impress. They were built to endure. They remind us that old solutions often solve modern problems better than anything sold as new technology. Understanding these designs gives both history enthusiasts and survival-minded individuals a framework for building systems that truly work under pressure. If this kind of historical insight with real-world application resonates with you, make sure to subscribe to Warfront Survival. Share this video with someone who values battle-tested techniques, and leave a comment on which forgotten system you want us to explore next. These lessons are more than history. They are tools to survive when failure is not an option.